Welcome back, everyone. If you saw part 1, you know we're rebuilding my old ray tracing project. Today, we're picking up right where we left off, and we're going to be making some serious progress on our render engine, so stick around. So let's get right into it. We will need providers for vertex descriptor, render pipeline descriptor, render pipeline state, and depth stencil descriptor. Don't worry if those terms are confusing, I'll explain them as we code. I'm just going to grab the render pipeline descriptor provider from the old project. It's way easier to tweak that than start over. A render pipeline descriptor sets up the rendering pipeline by defining crucial elements like the pixel formats for color and depth outputs, the structure of vertex data using a vertex descriptor, and the specific vertex and fragment shader functions to use. We're just using the basic render pipeline descriptor for now. We'll add more specific ones when we start working on the ray tracing renderer. The basic one will handle the solid renderer for now. Turns out my defaults for color and depth pixel formats were hanging out in a preferences file. And it's not here. Whoops. Let's just borrow that from the old project, shall we? This Swift style used here is a bit of a mess. Let's tidy it up. Much better. Let's get back to the render pipeline descriptor provider implementation. Looks like we're missing the MTL library definition in the engine. Let's add that in. Quick detour before we jump into the engine file. Let's switch to camel case here and change those function names from basic to solid. Okay, time to add the MTL library to the engine file. Looks like we need a vertex descriptor provider now. Let's add that next. A vertex descriptor defines the structure of your vertex data. It tells the GPU how to interpret the raw bytes, specifying the type and layout of each attribute like position, UV coordinates, normals, tangents, and bitangents. For example, it explains that the first 12 bytes are a float 3 representing position, and the next 8 bytes are a float 2 for UVs, and so on. I'm streamlining the vertex descriptors. Turns out, basic and read both use the same vertex setup, so there's no need for two different descriptors. We can just use one. Looks like SIMD3 is missing size, and the compiler's not happy. I think I added it with an extension in the other project. Let's get that fixed. Might as well clear out some clutter while we're here. Let's also rename basic vertex descriptor to default vertex descriptor. Perfect, that's done. Time to implement the render pipeline state provider. Think of render pipeline state as the finalized, optimized rendering configuration, built from the settings in render pipeline descriptor. Because the GPU needs time to compile these configurations, it's best to create them during app startup, then reuse them for fast rendering later. I'm refactoring the code to enhance clarity and adhere to modern Swift-style guidelines, which includes minimizing the use of forced unwrapping. Alright, let's get some shaders going. We're going to keep it super simple for now, just straight up pass the position through in the vertex function and paint the object pure white color. No fancy coordinate system and lighting calculations yet, since we don't have our camera or view matrices set up. Basically, I just want to see something on the screen, even if it's just a basic shape. Baby steps. Now, let's make a mesh provider. This will be our little toolbox for basic 3D shapes like cubes, spheres, the usual suspects. I'm thinking we'll grab these models straight from Blender. This provider will handle loading them up for us, so we have something to mess around with and test stuff. But for now, I will only be loading the cube. Before we continue with the mesh provider, let's take care of the mesh implementation. Okay, time to build our mesh class, which will be our engine's way of handling 3D models. Apple offers MDL mesh and MTK mesh, and while I haven't done a deep dive into the distinctions, we're going with MTK mesh since it's geared towards metal. And no, I'm not reusing my old model loading code. That was an experiment. I wanted to explore how files were read at the byte level, and yeah, it did work. Material parsing was slow though. I was parsing material files as strings and doing a ton of string manipulation, which wasn't exactly optimized. But when it came to complex materials and textures, things got way too complicated. So I switched to Apple's libraries, but even then, it was a Frankenstein of their code and mine. Yeah, even Apple's own libraries were a bit of a mess with materials, if I remember right. They'd kinda get some mappings wrong and just skip others. We'll use them for now, but we'll definitely have to figure out materials and textures properly later. For now, let's just focus on getting the shapes loaded, the basics. In my old project, I was just grabbing the raw MTL buffer data and ditching Apple's wrapper classes. But, thinking about it, those submesh wrapper objects actually hold some useful information, like the primitive type and index type. I was kind of just assuming everything was triangles in UN32 before, which isn't always the case, so this time, we'll keep those wrappers. Alright, let's get back to the mesh provider implementation. Let's grab the cubes object and material files from the old project. Time to set up all the providers in the engine initializer. I will quickly grab the depth stencil provider from my previous project as well. Alright, I think we're finally set to draw our first cube. Let's make a function for that. We'll build a solid mesh, and then, using the render encoder, tell the GPU to draw it. Alright, so for now, we're just going to grab the cube's mesh from the mesh provider. Then, we'll set up the vertex buffer with the render encoder. After that, we'll loop through all the index buffers and draw the primitives using that function. And hey, since I decided to stick with Apple's wrapper class for the submeshes, it actually hands us all the stuff we need for that draw primitives function, which is pretty sweet. Alright, let's fire it up. And it crashed. Classic. Okay, let's see what the error is saying. We forgot to set the render pipeline state. Easy fix. Let's get that in there and give it another shot. And another crash. This time, it's complaining about the depth attachment in the render pipeline being invalid. That's weird. Okay, after digging around a bit, I found the problem. Turns out, the depth pixel format in the metal view and the render pipeline state need to be identical. Makes sense, now that I think about it. Let's get those synced up and try this again. It's running, but it's just a blank screen. Seriously? No errors either? This is gonna be a pain to track down. Come on, what did I forget? Man, after a seriously long debugging slog, I finally got it working. And honestly, I'm still not entirely sure why. I started by wondering if the mesh loading was messed up, but even a simple triangle with hard-coded vertices wouldn't render, so I figured the shaders were the culprit. I looked, and everything seemed fine, so I started going over everything else. After checking and rechecking, I started rewriting files, one by one, to see if anything changed. And wouldn't you know it, rewriting the shader file fixed it. The weirdest part? The new shader code looks exactly the same as the old code that didn't work. Seriously, I'm just happy it's working now. I'm not going to dive into that rabbit hole and try to figure out the exact reason. Fingers crossed this kind of thing doesn't happen again. Okay, I know it's showing up as a flat square right now, but it's actually a cube. We just need to rotate it a bit so you can actually see the 3D shape. Let's get that rotation sorted out. We're going to make a solid class. It'll hold a mesh, basically the 3D shape, and let us set its position, size, and rotation. Plus, it'll have a handy computed var-named view matrix that automatically combines all those transformations into one matrix we can use. I'm just going to grab the math file from my old project. I don't want to get bogged down in the nitty-gritty of matrix calculations for position, scale, and rotation right now. Now, let's get back to implementing the view matrix for the solid. I'm going to add a new rotation helper to the math file that lets us set rotations for any axis with just one function, instead of having 3 separate ones. Let's get our drawCube function using solid so we can handle the cube's position, scale, and rotation. We will also be setting the solid's view matrix at buffer index 1 as model constants so that we can access this from the vertex function inside the shader. Alright, let's update the vertex function to grab the model constants too, and we'll also need to adjust the vertex position to factor in the solid's view matrix. Ugh, blank screen again. Turns out I accidentally set the object size to 0. So yeah, it was actually working fine before. My bad. Let's rotate the cube a bit and see how it looks. Something's not quite right. The cube looks like it's being clipped at the edges, and I'm not sure why. To get a better idea of what's happening, let's try animating it, make it spin. If there's something off, a continuous rotation should make it more obvious. So it looks like the cube's growing taller when it spins, but it's just a visual trick because we don't have shadows. Let's throw in the Blender monkey model to see if that's clearer. Then we can add some basic lighting to the shader and see what that does. Let's fetch the model of the monkey from the old project and load it inside the mesh provider. Yeah, it's looking off because we don't have shadows. Adding diffuse shading should make it look way better. Let's keep lighting simple for now. We'll pretend there's a light source way back behind the camera at 1000, 1000, minus 1000. To figure out how bright a surface is, we'll use the dot product of the direction to the light and surface's normal. We'll also use a saturate function to make sure the brightness is always between 0 and 1. And for a little extra light, we'll add a constant ambient brightness of 0.5. Alright, let's see how this looks. Okay, it's definitely better, but we're still seeing that clipping thing, and something else just feels off. I can't quite put my finger on it, but it's not right. Yeah, it's probably the camera. I totally forgot what the projection and view matrices do. Time to go brush up on that. Yep, figured it out. The clipping was because I hadn't set up the projection and view matrices yet. Metal's default view is basically a unit cube, which explains the clipping. And it's an orthogonal view by default, so everything's the same size no matter how far away, which is why the monkey head was looking a bit weird. We need to switch to a perspective view to get that things closer are bigger effect. The projection matrix transforms the view volume into an orthogonal space, and then the camera's view matrix converts that into Metal's final, canonical view space. Brendan Galea's video really cleared things up for me on view volumes and the math behind projection and view matrices. Feeling much more confident now. Let's get back to implementing this. I'm going to pull the camera class from my old project and tweak it a bit. To manage different camera setups, I'll also create a camera provider. Right now, we just need a standard scene camera, but later on, we can easily add cameras for animation recording or other specialized uses. Yeah, delta position and delta rotation don't really belong in that protocol, so I'm going to take them out. Also, DOF blur strength is a mystery to me. Maybe it's for ray tracing's focal blur. We'll add it back when we get to that. Let's remove it for now. We need a scene camera, so let's implement that. This will be our main viewport camera. For rendering, we can have a separate one. I'm just going to slap some random values in for now. We can fix them later. Or, just grab the good ones from the old project. Alright, let's wrap this up by creating a camera provider. It'll handle all our cameras and, like the name says, give them to us when we need them. We will create a scene constant struct that will store the details about the view matrix, projection matrix, and the camera's position. Okay, let's connect everything. We'll make a camera in our Swift code on the CPU side, then bundle its projection, view matrices, and position into a scene constant struct. We'll send that over to the GPU. Then, our vertex shader will use that data to transform the vertex position, basically going from our perspective view to the screen's canonical view. Seriously? Still looks exactly the same. I thought something would have changed. Gotta be a mistake somewhere. Let me take another look. Okay. Let's try grabbing the focal length and starting camera position from my old project, just to see. And, nope, now we've got nothing. Just a blank screen, wow. Let me check again. Wait a minute, the projection matrix was set to an identity matrix. That's definitely the problem. Let's fix that and run it again. Yes, there's a tiny object spinning. Okay, let's scale it up a bit. Much better, now we can actually see it. Looking good. The lighting and projection matrix really made a difference. Alright, let's get this monkey centered. After some fiddling, we're good. Let's see if this plays nice on Vision OS. And it does! Awesome! Oh, but the monkey head gets squished when I resize the window. Gotta fix that aspect ratio on the metal view. And there we go, all fixed. Wow, we've packed a lot into this one, haven't we? We've made some great strides, and while we've still got a ways to go before we're ray tracing dynamic scenes, we're definitely on the right track. Thanks for joining me on this journey. We're building something really cool here, and I can't wait to show you what's next. So stay tuned for the next video in this series. We're just getting started. Cheers!